We've already talked about how to write an equilibrium expression. So if we have some generic acid HA that donates a proton to H2O, H2O becomes H3O plus, and HA turns into the conjugate base, which is A minus. And so here's our equilibrium expression, and the ionization constant Ka for a weak acid, we already talked about the fact that it's going to be less than 1. So here we have 3 weak acids, so hydrofluoric acid, acetic acid, and methanol. And over here are the Ka values. So you can see that hydrofluoric acid has the largest Ka value. So even though they're all considered to be weak acids, right, 3.5 times 10 to the negative 4 is larger than 1.8 times 10 to the negative 5. So hydrofluoric acid is stronger than acetic acid, and acetic acid is stronger than methanol. But again, they're all considered to be weak acids relative to the stronger ones. So let's talk about pKa. So the pKa is defined as the negative log of the Ka. So if we wanted to find the pKa for methanol, all we have to do is take the Ka and take the negative log of it. So the pKa is equal to the negative log of 2.9 times 10 to the negative 16. So let's get out the calculator and let's do that. Negative log of 2.9 times 10 to the negative 16. And this gives us 15.54. Right, when we round that. So the pKa of methanol, the pKa of methanol is equal to 15.54. So we could write in a pKa column right here, and for methanol, it's 15.54. If you did the same calculation for acetic acid, you would get 4.74. And once again, if you did this for hydrofluoric acid, you would get 3.46. So as we go up on our table here, right, we're increasing in acid strength. So out of our 3 weak acids, hydrofluoric acid is the strongest, so it has the largest value for Ka, but notice it has the smallest value for the pKa. Right? So the lower the value for pKa, the more acidic your acid. So 3.46 is lower than 4.74, and so hydrofluoric acid is more acidic than acetic acid.